Problems 16, 17, and 18 are asking us the same things that 13, 14, and 15 were doing. We just need to graph the polar curves and see what they match. Instead, for 16, 17, and 18, though, it gives us a whole new set of graphs to pick from. So now we have r equals 2 sine of 3 theta. So we need to figure out what this graph looks like. So I'm going to go ahead and I'm going to start by finding the zeros. I already have my chart set up. So by finding the zeros, I end up with sine of 3 theta is equal to 0. So anywhere sine of 3 theta is equal to 0 will give me a 0 on my graph. So in this case, if I take the arc sine of 0, that tells me that 3 theta is equal to 0, pi, and 2 pi. So right off the bat, I have a bunch of zeros at 0, pi over 3, and 2 pi over 3. However, my zeros should extend within a domain of 0 to 2 pi. So I can actually keep this going and I can actually come up with more values. So in this case, pi should also satisfy it because sine of 3 pi is equal to 0. 4 pi over 3 should also be a value. 5 pi over 3 should also be a value. That would give me sine of 5 pi. And then 6 pi over 3, which is 2 pi, should also give me a 0. So technically, these are all my zeros. However, 0 and 2 pi are obviously the same solution in this case. So we only include it once. Or actually, in this case, we can write it twice, and we should just come back to that point after graphing it. So I'm going to go ahead and I'm going to write out some of these values. So it is 0. I know that I have a radius of 0. At pi over 3, I know that I'm going to come back to a 0. So I'm going to write pi over 3 here, but I need to pick a point in between that's non-zero, because if I just write all my zeros down, I'm not going to have anything on my graph. So I'm going to pick pi over 6 in this case. I'm going to pick something that shows me how my radius should be extending. So 2 pi over 3 is also a 0, but again, I want to pick a point in between because I want to see what this graph is actually going to do. So if I go ahead and try to find a point in between, pi over 3, let's plug in pi over 2 and let's see if that gives us anything. That should give us something. That is in between those values, so that should give us a non-zero value that tells us what this graph is going to do. So pi over 3. Pi was another one of my values, so I'm going to pick a value in between, see if I can figure out what it is. Again, I'm going to pick, I'll pick 5 pi over 6 in this case. Now, let's go ahead and let's graph out some of these points and let's see what the graph is doing. This might be enough points, it might not be. The only way to tell in this case is really to kind of graph it out. Again, we have a sine of 3 theta, so this is going to be one of those multiple petal equations. And because the number is odd inside of the trigonometric function, that will be the amount of petals that we need. So as soon as we get 3 petals, we know that we're done with this graph. Consequently, if this was an even number, if this was like 2 or something, it would have 2 times that amount of petals. So sine of 2 theta, we would be looking for 4 petals in that case. But because we're sticking with 3 in this case, 3 is just 3 petals. So let's go ahead and figure out some of these values. So at 0, I know I start with a value of 0. Pi over 6, when I plug that in, I end up getting 2 times sine of 3 times pi over 6. That is 2 times sine of pi over 2. Sine of pi over 2 is 1, so my radius is actually 2 at that point. So that means that at pi over 6, I extend out this way. I hit one of my loops, and then for pi over 3, I actually come back around. Pi over 2 gives me sine of 3 pi over 2. Sine of 3 pi over 2 is negative, so this gives me a radius of negative 2. So this tells me that at pi over 2, I actually have a negative radius, so I'm going to go this direction. I'm going to flip it across its axis. So I actually have a petal that is centered around here. And again, I was going in this direction. So I started here, went from here to here, I came back around, and I came back to my origin at 2 pi over 3, which was a 0 value. 5 pi over 6 should be a non-zero value because pi was a 0 value. So at 5 pi over 6, I end up getting sine of 5 pi over 2. Sine of 5 pi over 2 would be, so if I have a unit circle, I would have pi over 2, 3 pi over 2, 5 pi over 2. So 5 pi over 2 is going to give me a positive value of 1. So this will have a radius of 2 in this case. So I come out from here, I extend my pedal out, and I know that at pi, it comes back in. Good. So in this case, again, because I know that I should only have 3 pedals in this case, I can actually stop here. If I go any further, what I end up doing is I actually just end up tracing the same graph over and over. So if I was to choose something past pi like 5 pi over 6, or not 5 pi over 6, it would have to be like 5 pi over 3 or something like that. What I would end up finding is that I would actually trace the same exact graph over and over. So this can be a good shortcut to recognize that when you need to stop, you know that you've reached the amount of points when you reach the same amount of pedals. So in this case, because I have n equals 3 as my value, I should only have 3 pedals. So because of that, I know that this graph fits. And there's only one graph on the page that actually matches this, and that's E.
The Teaching Center, UF's Learning Resource Center.